Sorry, my last video cut off. Anyways, so where we left off, we were talking about maximum and minimum rates. So from our dot product rules, we know that the dot product of two vectors is equal to the magnitude of both of those vectors times cos theta, where theta represents the angle that is formed between those two vectors. So if we want to find the maximum rate, the unit vector that we would use to define that is u is equal to positive our gradient f over the over the magnitude of that value, where the magnitude equals the rate, so maximum rate, right? And on that same note, if we want the minimum rate, this would be represented by the unit vector of negative of our gradient function over the magnitude. So let's explain this further with an example. Okay, awesome. So given this function here, at a specific point, find a unit vector in the direction in which f increases most rapidly at p and determine the maximum rate of change. Okay, so we're determining maximum rate of change, so let's start with I. Okay, so let's start with our partial derivatives at our point. So we're going to get our gradient. This is, okay, so we got, this is our x term first. This is negative 6x squared, our first one. And then with y, this is negative 3y. And for our z term, this is 2z. Okay, and this is at point x equals 1, y equals 1, and z equals negative 3. So this then becomes, this is negative 6 times 1, so this is negative 6, negative 3, and this is negative 6. So then when we find the unit vector, so the unit vector, we want it to be for our maximum, so this is positive. So we're going to take our gradient for our vector that we just found. We're going to put it over the magnitude of what that would be. This is going to be equal to, so we have negative 6, then we have negative 3, negative 6, and this is over 36 plus 9 plus 36. This is 36 plus 36 plus 9. Oops. And this just becomes the square root of 81, which is just 9. So this is negative 6 over 9, negative 3 over 9, and negative 6 over 9. And if we make this into an equivalent form, which is divisible by 3, so this is negative 2 over 3, negative 1 over 3, negative 2 over 3. Okay, so this is our unit vector, and we want the maximum rate of change. So the maximum rate of change, so max rate of change is equal to our positive gradient magnitude. So that was the denominator, and we said that was square root of 81, so this is equal to 9. Now for part 2, if we are finding the minimum rate, so then minimum rate is going to be negative our magnitude. So if it was 9 for our maximum, it is now our negative 9 for our minimum rate. And then our unit vector is now negative, so this is going to be So negative the unit vector that we found in the previous example, so in the previous part. And if we distribute that negative in, this is 2 over 3, 1 over 3, and 2 over 3. Okay, so those are the two answers to our question. Right, so this means that if we were to draw this out on a number line, the maximum and minimum rate represent our end caps. So we can only have stuff going on in this region here, right? If we're given a rate that is outside of these regions, then it is not valid. Okay, so now we're going to talk about implicit differentiation. So this is a way of writing our functions and relating our functions and variables that they are with respect to, and putting them into a determinant sort of matrix to help solve for the Jacobian determinant. So if I wanted the Jacobian determinant of these two functions here, so we have functions f and g, where each one is with respect to x and y, so they are functions of x and y, you would put the first function on top, in the top part, and then in the top row, in the denominators for these parts, you would put the two variables it's with respect to, and then in the bottom row, you're taking the partial derivative of the second function. So this works with however many functions you have, and determinant is multiplying this way minus this. Right? And if you have 3, you're multiplying it like this. You cover these ones up if you wanted to do it for this specific one, and then you're multiplying it by this times this minus this times this. You should already know this though from 211. So I'll talk us through an example. So if we're given a function of f and g, and each is with respect to, let's see, okay, and each one is with respect to r and theta, we are asking for what this is. So this is our Jacobian determinant. So that means we're going to place our function f at the top row, right, derived with respect to each of these functions here, so each of these variables. And the same is done for g. And here's what each one represents. So we're going to find the partial fractions for each one. We're going to replace it in that place. And then when we find the determinant, so this is r times cos squared, and this is minus negative. So minus negative means it will turn into a plus. And this is r sine squared. So we know that our identity cos squared plus sine squared theta is just equal to whatever coefficient it has. So this gives us j equals r. Okay, so if we have 3 functions, we'll be making a 3 by 3 one. And we have a value for theta this time. So in this case, each function is with respect to theta, phi, and rho. So these are the 3 ones that we're going to use. So in this case, we will be plugging in for our theta, because we're given theta equals 0 here. So once we have written all of this out, so this is just each partial derivative written out in this form. Once we substitute for theta, we see that there is this row here. So we are only going to use this one. So that means we block off this row. this column, we block it off, and whatever's next to it. So then this becomes rho sine phi, and times this determinant. So this is negative rho sine squared, and this is minus rho cos squared. And this is negative, because we're using the second row, because if we use a column, this goes positive, negative, positive, just like the rows goes positive, negative, positive when we're using that coefficient. Sorry, I ran out of room. And this will give us, so if we simplify this, this is just going to be negative rho, right? Because we can take that rho out, so let's do that. So this is sine phi, and this is, so take the negative rho out, sine square phi plus cos squared phi. And this just means this is negative rho squared sine rho. Positive, actually. Right, and this would be our answer. Okay, so that's just a different way to work with multivariable functions. But it's important to note, in order to solve this determinant, you need to have the same amount of variables as functions, or else it won't work. So another method for implicit differentiation, if we are given two functions, f and g, each with 5 variables, there are 10 different combinations, 10 different sets that we can write out to define our equations. So they're all written out here, so you can just take a look at them. So what if we wanted to find the partial derivative of u with respect to z? So we would want to find equations that have u as the prime function with respect to z. So z has to live in there somewhere. So that gives us 3 equations to choose from. Right, so we can use either of those 3 and then solve using that. So if we were to draw this out, so here's how we can use our tree diagram from chain rule. So I'll try and explain this in a different example. So if we're given u and v, each of them with respect to x and y, right, as functions of x and y, and we have 4 variables, we would define all those variables up here, but since x and y aren't given, they just end at these branches. Whereas since we're given u and v are functions of x and y, we split those off into our branches to get those. And if we wanted to compute the partial derivatives, and say if we wanted to compute our partial derivative of w with respect to x, we would have to take each one of these paths. So we'd have to take this path here, so df with respect to dx, and then we would use our multiplication like we did with our chain rule. So we have dx here, which came from our df du, so this would be plus df du times du dx. You can see that the du is going to cancel to give df over dx. And then this would be added to, so we've got another one where our dx lives in the bottom. Then we would use those two, so this is df over dv and dv over dx, and the dv is going to cancel out, and this would be equal to 0. Right, so that's how you can use the chain rule tree to use implicit differentiation. Okay, So assume that we have this system here. So when we're given this equation, we're asked to find our partial derivative of y with respect to x. So there's a different way to do this. We can instead say that this is our negative. So let me highlight this color. So we're going to flip these around and put our function with respect to x partial derivative on top, and we're going to switch our y to put this partial derivative on the bottom. So by doing that, this makes it a lot easier to solve because it's equal to negative. So with respect to x, this is 6x z to the 4, then 6 z 4, and this is minus, actually, before we go forward with that, I'm going to rewrite this equation just to make it a little easier to work with. So I'm going to rewrite this. This is going to be plus 4 z is minus 14 so 14x minus 1 y, and this is plus 8xz plus y cubed z equals 0. Okay, so when we do our equation, so we're going to do with respect to x first. So this is going to be negative 6 over x, and this is going to be negative 14y plus 8z, right? And that is our numerator. And in the denominator, we're doing with respect to y now. So this is going to be, so these are both constants. This would be negative 14, it's x minus 1. And this is plus 3y squared z. Okay, so we're given our point, but we don't have what y is equal to. So at our point we have x, we don't know what y is, and our z is equal to 1. So we have x equal 1, y we don't know, and z equal to 1. So I'm going to do a little side mission. We're going to find what y is. So find y. So we're going to plug in our values of x and z in our original equation. So this is ln 1 to the power 6 times 1 to the power 4 minus 14, and this is 1 minus 1 times y, and this is 8 times 1 and times 1 again, so that's just going to be 8, and times z is 1, so this is going to give us, so this is 0 minus, it's also 0, it's plus 8 plus y cubed equals 0. So we're going to move that 8 over, so negative 8 equals y cubed, and then y is equal to negative 2. Okay, so we're going to write that in. Equals negative 2. Okay, so then that gives our answer as, so once we plug in our values, so this is 6 over 1, 14 times negative 2, and 8 times 1. This is times 1 We have negative 2 squared in our y. Then this is multiplied by our z, which is 1. Okay, so when we do this, this gives us negative 6 minus plus 28 plus 8. And this is over, so this becomes 0, and this is going to be 12 in the bottom. And this is equal to, so 6 plus 28 plus 8 divided by 12. It's going to be negative 42 over 12, which is equal to 21 over 6. Sorry, we can simplify that a little more. This is negative 7 over 2. Okay, so now that we have this relation, we want to find dy dx. We're going to use the same thing that we did before. I think I might be missing something. Hold on. Okay, so this one we're not given a point, so we are just going to solve with our variables still in there. So we're going to find our, hold on, so this is dy over dx. We're going to do a little flip. We're going to put our x on top, our partial derivative, and our y on the bottom. So when we do this, this is equal to negative. We start with our partial derivative x. This is 3x squared, y squared, plus. This is going to be sine y plus e to the x y cubed. Oh, and we want this equal 0, so if we just move that 3 to the other side, it doesn't matter because it's just going to be 0 anyways. Okay, and then when we do with respect to y now, this is 2yx cubed plus x cos y plus 3y squared e to the x. And this will be our answer. Let's distribute that negative in. And then so each of our terms becomes negative in that case. Okay, so that is it for this question. Okay, so that brings us to the end of the notes section of this video. So in our third part of the video, we will be going through some example problems and applications of these different topics, which were implicit differentiation, maximum and minimum rates, as well as using our chain rule a little more and talking about, what's the first thing we talked about? Hold on. And talking about directional derivatives. So we're going to put those to use in our next few examples. See you there.